Welcome! Today we're going to do the gradient vector and the directional derivative. Gradient vector, or simply gradient of f, is a vector with the partial derivatives as components of that vector. If f is a map from two space to the set of real numbers, then the gradient of that function f, denoted by this triangle f, grad f, that is the simple nabla, right? So if we have a function of just two letters x and y, then the gradient vector is two-dimensional, given by the first component being the partial derivative of f with respect to x, and the second component being the partial derivative of f with respect to y. So this is a vector. This is the unit vector in the direction of the x-axis, I, and sometimes we put a hat on that. And j is the unit vector in the direction of the y-axis. Sometimes we put a hat on that. So the components of those are fx and fy, right? But I tend to write this like this. Separated by a comma, but I mean a vector, so if you want to write that as a vertical vector, go ahead, that's totally fine. I do this because it's easy. But the problem in it is that these look like points, and I don't mean points, so you'll have to distinguish that through the context of the problem. Okay, example 3.1. Find the gradient of the function f of x and y, where f is equal to x squared minus 3 in brackets y minus 1 squared plus 3. Okay, so let's take f subscript x, the partial derivative of f with respect to x. Well, let's see, we have 2x, right? Because we're treating y as a constant, and the derivative of a constant is 0. Now, f subscript y is, again, treating x squared as a constant, because we're treating x as a constant. Well, the derivative of x squared with respect to y partially is 0. The derivative of 3 with respect to y partially is 0. So we're really just differentiating this. Now we would use the chain rule, right? We're pulling down the 2, so we'd get minus 6, y minus 1, and then multiplied by the derivative of the inside, which is 1. So we would get minus 6 y minus 1. Okay, then in this case, we've got 2x times I hat minus 6 y minus 1 times j hat, and I like to write this as 2x comma minus 6 y minus 1 bracket, right? But again, if you want to write this as a vertical vector, go for it. Similarly, for a function of 4 letters, x, y, z, and w, grad f, nabla f is f subscript x, f subscript y, f subscript z, f subscript w. Or, just by transposing that, you can put it like this. Just be consistent in the problem you're doing. Definition 10. Let f be a function of x1, x2, etc. up to xn. So suppose we have a function of n letters. Then the vector grad f is given by the partial derivative of f with respect to each of those letters, and so it's given like this, right? So now you might see the advantage of writing this horizontally, because otherwise this can be quite large and take up a lot of space on the page. Grad f is called the gradient vector, and we say grad f when we refer to this. The directional derivative of the function f at the point P in the direction of the vector v is given by this formula here. So f subscript v at p is grad f at p dot, now that is the dot product of v over the norm of v. So here v hat is 1 on the norm of v times the vector v is the unit vector in the direction of the vector v. So this vector right here, which is this one, has norm equal to 1. So when you take the dot product of this vector with grad f at p, what you get is the slope of the function at p in the direction of that vector v. Now a point to note here is that that v has one less dimensions than the space you're in. So for example, if you have a function of x and y, well then you're viewing this in a three-dimensional space. You've got z is a function of x and y, but the vector v would be given as a two-dimensional vector. So this is like if you are on the side of Mount Coolum, for example, and somehow you have a compass that can tell you which direction is uphill, well that would be telling you that in an xy direction, not a three-dimensional direction, right? It tells you which way you go in order to go uphill. All right, but we'll come to this notion soon. So let's have a look at example 3.2, and I'm going to show you some graphics here on the left. Find the directional derivative f subscript 1 comma minus 1 at the point 0, 1 for this function f of xy is x minus x squared y squared plus y. And so what I want to show you after doing this calculation is a way to visualize all of this. Okay, so let's do the calculation first. So we've got the vector v. Now this is a two-dimensional vector. It is the vector 1 minus 1. So this is the direction we're looking when we're calculating the slope. Okay, so next let's take its norm. The norm of v is equal to the square root of the sum of the squares of the entries. So 1 squared plus minus 1 squared. And 1 plus 1 is 2, so we've got root 2 as the norm of v. Okay, now let's construct the unit vector v hat, which is 1 on the norm of v times the vector v. And so we have 1 on root 2 times the vector 1 minus 1. Okay, now to calculate the directional derivative or the slope of the function at p in the direction of the vector v, well, we need to take a dot product with grad f at p. So we need to calculate grad f. So grad f is equal to f subscript x comma f subscript y. This is a vector. Okay, so the derivative of this function with respect to x is, so the derivative of x with respect to x is 1. The derivative of minus x squared y squared with respect to x partially is minus 2x y squared. And then the derivative of y with respect to x partially is 0. So that's f subscript x. Now f subscript y takes the partial derivative of this with respect to y partially, so the derivative of that x is 0 with respect to y partially. The derivative of minus x squared y squared with respect to y partially is minus 2 x squared y squared. We're treating x as a constant there. And the derivative of y with respect to y partially is just 1. Okay, now evaluating this at the point p equal to 0, 1, we're just subbing in x is 0 and y is equal to 1 in this formula. And we've got, let's see, x is 0, so this is just 1. If If we put x is 0 here, we've got 0 for this part, and then we've got a 1 there. So 1, 1. So we have the vector 1, 1. All right, and so next we need to take FV at, what was the point again? Where was it? P is 0, 1. Okay, so F subscript V at 0, 1 equals grad F at 0, 1 dot, that's the dot product, 1 on root 2, 1 minus 1. Okay, so we can pull this out the front because it's just a scalar. Now this one right here, we deduced that that was 1, 1. So we've got 1 on root 2, 1, 1 dot 1, minus 1. And so that dot product, remember we take this times this plus this times this. So we've got 1 minus 1 is 0. 0 times 1 on root 2 is 0. So that slope or directional derivative in the direction of the vector v is 0. All right, so now that we've done a basic calculation on this, let's visualize this geometrically. So I'm going to open up this, and you can see I've written a bunch of code. All right, so the first parts, this is the part we can edit. All right, so put a space there. I'm going to run this. And so what you see here is I've entered the function f. I've entered the point p, or at least the x and y coordinates of it, right? Because it's really a three-dimensional point. Then I've entered a multiple of that vector just so I make my arrow bigger in the diagram. All right, so it's parallel to this v, but it's a slightly different v. All right, so let's run this, and then I'll describe to you what we have. All right, so the first thing that this code has output is the equation of a vertical plane parallel to the vector v. So I should really say that. So I'm going to edit that. Where was this? Oh, I can't really find it. I'll do that later. Okay, so this is the equation of the plane that is parallel to that vector. All right, so the gradient vector is calculated this as the vector 1, 1. And then it's calculated the directional derivative as 0 for this particular surface, point, and vector v. All right, now for the geometric picture. So this yellow surface that you see is this surface right here, z equals x minus x squared y squared plus y. That's the surface. Now this black point that you see here, and I'll turn it a bit so you can see that possibly better. That black point there is the point P, which is the point 0, 1, and then there's a height of that function, or a height of that point as well, right? So that's just obtained by subbing in x is 0 and y is 1, and so we get out 1 when we do that. So it's really the point 0, 1, 1. Okay, so we've got our point, we've got our surface. The green plane that you see here, that is a vertical plane parallel to this red vector v, or a multiple of v as I've chosen here to make it bigger. So that red arrow is the vector v. That is a two-dimensional direction. You see, if I move this, you'll see it doesn't have a height up or down, right? So no component in the z direction. It is a two-dimensional direction. So if you wanted to take the slope of this surface in the direction of this red vector v, what you would be doing is taking the slope of this slice through this surface, this vertical slice through the surface in the direction of that vector v, you'd be taking the slope of that intersection, or the curve of that intersection, right? What is the slope at P, or this black point, of the slope of that intersection? Now, I've also drawn a tangent line in blue, in dashed blue, right? So we worked out that this slope is 0. So what is the slope of this dashed horizontal line? Well, we see it's horizontal, right? That is showing 0, but this is a bit of a coincidence here because ordinarily the two of these, you know, the blue line and the red arrow don't coincide, all right? So here in this example, they do coincide, but let's just call it coincidence. Okay, so let's go ahead and change some values up here. I want to leave the function the same. So what if I just change the position of the point? What if I make this 1, 1? Okay, so let's have another look. All right, so it's gone on the other side now. The vector v is still the same coming out of that point. All right, so I turn this around. Now what we have is, well, it's just changed position, but it looks like that slope is still coinciding and equal to 0. So I've got to change a few things to make that look different. So let's put a -1 here. Okay, so now I can see the blue dashed line is no longer vertical. So this is a better example. All right, so let's have a look. Turn the orientation of this so we can see this properly. All right, so what we have here, we have a two-dimensional XY direction in the arrow that's red. That's the vector v that we're seeing there in red. The black point right here, that's our point P. Okay, so we are asking the question here, or displaying, what is the slope of this surface in a vertical slice that is parallel to the vector v? Right, now we can see that that slope is some number other than 0. So what do we have? We have the slope being -2√2. That's the slope of this blue dashed line. Okay, which is a tangent to the surface at the black point P. So I hope it is a bit more clear to you what this directional derivative is. It's a scalar or a number, and it represents the slope of the function or the surface in the direction of the vector v. Right, but to properly visualize that, that is a tangent line on a vertical slice that contains that vector v, or is parallel to the vector v. So you can see this really does involve a lot of geometric thinking, so it's incredibly helpful to be able to visualize this. I'm going to make this little piece of code available to you so that you can play around with it, but I recommend just edit these 3 lines up here, right? And don't edit the code below, because that's the code that makes all of this visualization work. All right, let's move on to the next page. Okay, so I've told you that the directional derivative here is definition, but that's not totally true. So sorry about that, but it does kind of make it simpler if I tell you it's a definition. So let's just take a little moment to go into how it's a consequence of another definition. Okay, so I will move over to my next page. So it's a consequence of the following definition. So let v hat be a unit vector, meaning that it has norm 1. And let P be the point x0, y0. We've omitted the z coordinate here because I want to view this from the point of view of contour diagrams. But there's a z0 in the 3-dimensional version of this point. Okay, now remember, these vectors, when we're calculating the directional derivative, have one less component than the dimension of the space that that surface lives in. So the real definition of the directional derivative is given by this formula. So we have f subscript v hat is the limit as h goes to 0 of 1 on h, f of x0 plus h times a, comma, y0 plus h times b minus f of x0, y0. So what's happening there is we are stepping in the direction of the vector a scaled by h. And so this is a rise over run formula. Okay, so the rise then is the value of the function here up above minus f of x 0, y 0. So that's our rise. And our run is h. okay, because the length of this vector right here will be h, given that v hat is a unit vector. Okay, so I'll start to fill in this diagram here, and I need to write pretty small. So this vector here is the vector h times v hat, and then we'll note up here that the norm, or the length, or the magnitude of this vector is the absolute value of h times the norm of v hat. But since the norm of v hat is 1, we just have the absolute value of h for the magnitude of this little vector right here. All right, and so as h gets small, this gets small, and hence the length of this vector gets small. All right, so let's talk about f. Where is f in this diagram? So this curve that you see here is a contour of f passing through x0, y0. Okay, and so this point here is the point P, which is x0, y0. Okay, so what is this point? Well, that's the origin. So 0, 0. And then this vector right here is the vector OP, which tells you how to get from the origin to the point P. All right, now this vector here will be OQ, where this is the point Q. And so the point Q is x0 plus h times a, comma, y0 plus h times b. And so this is OQ, or how we get from the origin to the point Q. Okay, so, and this f again being a contour of a three-dimensional surface. So we step out in the direction of the vector v, a distance of h units, and that's our run in the calculation, the length of this. The rise in the rise over run is, you know, this difference up here from the value at the function to this. All right, so it's a rise over run calculation, so let's note that here. Rise over run. But then we're letting that h, the distance of this, tend to 0. Now you'll notice that this definition is very similar to the definition that you know of the first derivative by first principles. Okay, so let's note this. The point Q satisfies this vector equation, OQ equals this as a vector, which is OP plus h v hat, right? Just as we have in the diagram here. So the expression on the right-hand side of our limit is of the form rise over run. Now have a look here. So let's do some calculations to come up with this other formula that we have on the previous page, right here. All right, so what we want to notice first is that f is a function of h, and, well, it's a function of h, right? Because presumably x0 and y0 are numbers, and a and b, the coordinates of that unit vector v hat, they're also numbers. But h here is a variable, and so what we have is a function of h. All right, so in particular, g is f of all this stuff, so g of h is f of q, and g of 0, that is when h is equal to 0, if we sub in 0 here, then we have f of p, or f of x0, y0. Okay? And so that gives us this, right? So in other words, we can look at this limit right here as the limit as h goes to 0 of 1 on h times the difference of f at q minus f at p, except f at p is g of 0 and f at q is g of h. All right? So this is the same thing as we have here, except using what we have over here in the column. Okay, now what is this? This is the first derivative. Remember your first principles definition of the first derivative. So we have g dash, but it's evaluated at h equals 0. So I'm going to write in h equals 0 here to avoid confusion, or g dash of 0. Right, so what this is it's the derivative of g with respect to h evaluated at h equals 0. Okay, now another point of view on this is that we have the derivative with respect to h of f of x0 plus ha, comma, y0 plus hb evaluated at h equals 0, which equivalently is evaluated at x0, y0. Okay? So for this one, since this is a function of h, right, the input values, x is a function of h and y is a function of h, we can use our multivariate chain rule and say then that this is equal to the derivative of lowercase f with respect to x evaluated at x0, y0, and then multiplied by dx on dh. Okay, plus partial derivative of f with respect to y, again evaluated at x0, y0, multiplied by dy on dh. All right, and so this is the chain rule for partial derivatives when the inputs are also functions of another letter, in this case h. Okay, now dx on dh, we can just see this being the derivative of this just being h, and this one right here, we can write this in a different way as f subscript x at x0, y0. And then all of this multiplied by h, because the derivative of this right here is h. You know, differentiating x0 plus ha with respect to h, we have h. Okay, similarly for this one, the derivative of this with respect to h is h, and so we can write this. Oh, sorry, no, that's a, isn't it, over here? That's a. And then this one with respect to h is b. So we can write this f subscript y, x0, y0, multiplied by b. Okay, now we're getting somewhere. So this we can view as a dot product. So it's the dot product of grad f evaluated at x0, y0 dot the vector a comma b, and so then this is grad f at x0, y0 dot v hat. Okay, and that is the formula we presented as a definition earlier, but it's really a consequence of the first principles definition of the directional derivative, right? So this here is v hat, right? It's a unit vector because we've taken v and divided throughout by its norm, And so this here is a unit vector. Let's call it v hat. Right? This is grad f at p, matching what we have here. Okay? So let's go and say that this is really a consequence of this being a limit. As h goes to 0, 1 on h, f of x0 plus h a y0 plus h times b, subtract f of x0 y0. Okay. So the directional derivative f subscript v at p gives the rate of change of f at p in the direction of the vector v. And so you can think of this possibly in a more abstract sense too. Like, for example, if you have a metal plate where the temperature of that metal plate depends on the position in the plate, well, you might ask the question, what is the rate of change of the temperature in some particular direction? Okay, and so you would use the directional derivative for that. Okay, example 3.3. Consider the function of x and y given by this. So there are fourth powers in there, and let p be this point. On that surface, the gradient vector is this, all right? So we can do that just by taking partial derivatives. Evaluating grad f at p gives us this vector right here, and we can display it like this if we want to. Okay, see the figure 16 and 17. So what we see here is there's our point P, here's our surface, and this is probably the direction of the vector v. No, because we haven't given a vector v. So this is just the gradient vector, right? This is the gradient vector here. So let's label that in our diagram. This is grad f at p. Okay, so what does that on its own mean? What does it give you? Well, it tells you the direction to go in order to ascend or go up the function at the fastest rate possible. Okay, so let's write this here in the column. Grad f at p is the vector in the xy plane that indicates the direction to go in order to ascend f most rapidly from P. All right, so back to what I was saying earlier, if I'm on Mount Coulomb, maybe in your case Mount Kutha, and I have a rather unique compass that tells me which direction to go in order to go uphill. So it doesn't tell me in north-south direction. It tells me which direction in the XY plane to go in order to go up that mountain most rapidly. Right? So that would be grad F. All right, so there are a number of things associated with this concept which are important. But let's have a look at theorem 3. Grad F is a vector whose direction indicates the direction in which the maximum rate of change of F is achieved. Right? So that's another way to say this. Okay, so now what we have in the next picture, we've got the function, and this is a little bit difficult to see here. But what I've got here is that arrow. So this is grad F, right? And here's the same grad F looking from above. So we'll call this from above. and this is a contour map or diagram, let's call it. Okay, so all of these little loops that you see on this are positions on this surface where you have equal elevation. So for example, if you walked around the surface in this pattern looking from above or from below, along this curve you would not be increasing or decreasing in elevation. Likewise here, you would not be decreasing or increasing in elevation, but perpendicular to that, you would be increasing or decreasing in elevation most rapidly. Okay, so in other words, grad f at P is perpendicular to a contour that intersects P. Okay, now parallel to the contours, no change in elevation, let's say. Okay, and so if I highlight this, it's really hard to see on my printout, but I'm going to highlight, because it's dark gray on the printout, maybe yours is in color. So I've highlighted with my pen here one of these contours. So let's just suppose is this one. All right, so I'll see if I can highlight this same one so you can see how those correspond. So let's say this, looking from above, is this, and maybe rotate it around as well. Okay, so this tells you again, and it's this arrow here, grad f, is perpendicular to the contour, but it tells you which direction to go in order to ascend, go up the function most rapidly. All right, now perpendicular to that would be no change happening there in this direction or in this direction. Okay, so reiterating what we've said for z equals a function of two letters, x and y, two important properties of the gradient of a function are the following, and I'm sure we've already said that, but let's read it out. The gradient grad f at AB is perpendicular to the contour through AB and points in the direction of increasing f. In fact, the direction and magnitude of steepest slope at AB are given by grad f at AB, and the steepest slope is the norm of that. And this here is a direction, or indicates a direction of that steepest slope. All right, so we can understand these two facts by considering the value of cos theta in this expression. Now I'll remind you from other courses that A dot B is equal to the norm of A, if A and B are two vectors, times the norm of B times the cosine of the angle between them. Theta is the angle between vectors A and B. Okay, so not these A and B, because these A and B are referring to the point if we have vectors. So this is, I'm just reminding you of this identity for vectors. The dot product is the product of the norms times the cosine of the angle between them. Okay, so here we have a vector A and a vector B, say, right? A being grad f and B being v over the norm of v. So we have then, since this is a unit vector having norm 1, it's the norm of this one there times the norm of this one, which is 1, times the cosine of the angle between them. So where theta is the angle between grad f and the unit vector v hat, which is 1 on the norm of v times the vector v. Okay, the directional derivative or slope in the direction of the vector v when v is equal to the gradient of v. So we're going to take a particular case. So what we're doing here is considering the case when that vector is just equal to the gradient vector at P. All right, in what follows. All right, so let's have a look at that special case. So then when v is equal to grad f at P, we have the directional derivative f subscript v at P is equal to the dot product of grad f at P with v over the norm of v. But v is equal to grad f P in our case. All right, so what is this? Well, let's sub that in. We've got grad f at P over the norm of grad f at P. Okay, so now this is a scalar, so we can pull it out in front and put it on the left. So we've got 1 on the norm of grad f at P multiplied by the dot product of grad f at P with itself. All right, now remember, if A is a vector, then A dot A is equal to the norm of A squared. All right, so this right here is the norm of grad f at P squared. Right, but now that's a scalar, you see, so a square divided by the same thing, well, we can just cancel one of those and we end up with the norm of grad f at P. Okay, so what we've deduced then is that f subscript grad f at P of P is just the norm of grad f at P. Okay, so what does this tell us? Well, now let's just put this remark in a box. So now if v were not equal to grad f at P, then f subscript v at P being the norm of f, or sorry, the norm of grad f at P times cos theta, this would have to be less than the norm of grad f at P. Right? And why? Because cos of theta is between -1 and 1. Now where do I put this? Okay, let's put it in another little box here. So cos theta is less than or equal to 1, greater or equal to -1. Okay, so this would have to be, when they're not equal, it would have to be strictly less than this, because cos theta would be strictly less than 1. Okay, so in other words, if you deviate in direction from grad f at P, well then you get a directional derivative that is less than grad f, or less than the norm of grad f at P. All right, so this tells you then that the direction grad f of P, in that direction, you achieve the maximum. You achieve the maximum, and that maximum is the norm of grad f at P. Right, so it confirms what we saw on the previous page. In other words, this. The magnitude of steepest slope at the point AB is given by the direction of this vector and is this value. This is the value of that slope, the steepest possible slope. Okay, let's move on to example 3.4. All right, so in 3.4, find the directional derivative of the function g, which is e to the x squared cos of y at the point 1 comma pi in the direction of the vector minus 3i plus 4j. So this is minus 3, 4, right? This is a vector. This is a point. Right, same notation, different entity. All right, so what do we do? Well, first we need to calculate grad g. All right, so this is the vector, partial derivative of g with respect to x, partial derivative of g with respect to y. Okay, now differentiating this with respect to x partially, we are treating y and hence cos y as a constant. So we've got cos y times the partial derivative with respect to x of e to the x squared. And then taking the partial derivative of this with respect to y, then we're treating x as a constant. And so we can pull that out the front of our differential operator and differentiate cos y with respect to y. So we get minus sine y. So we have minus e to the x squared sine of y for that. But we've got to do a little bit more here. What is the derivative of e to the x squared? Well, we need the chain rule. So we have to also differentiate x squared with respect to x and multiply that by that. So we have 2x cos of y times e to the x squared, and then the derivative with respect to y, we'll just copy this down again. Okay, so now we have grad g, but we need to evaluate it at 1 comma pi. So grad g at 1 comma pi. So now we are subbing in x is 1 and y is pi. All right, so cos of pi is minus 1. So we have 2 times 1 times minus 1 and then times e to the power of 1 squared, so times e. Okay, here sine of pi is 0. So, and e to the power of 1 squared is 1, so we've got minus 0, so we just have 0 there. All right, so let's simplify this. We've got minus 2 e comma 0 as our gradient vector at the point 1 comma pi. Okay, now we need to find our unit vector in the direction of minus 3, 4. So we've got v equal to minus 3, 4. And so v hat, the unit vector, well, we just divide by the norm of the vector v. And that norm is 5 because the square root of 3 squared plus 4 squared is 9, plus 16 is 25, the square root is 5. So 1/5 minus 3, 4. Okay. All right, so now taking the directional derivative, so g subscript v at the point 1 comma pi is equal to the dot product of grad g at 1 comma pi with the unit vector v hat. Okay, so we have then that vector minus 2e comma 0, and then we're dotting that with 1/5 minus 3 comma 4. Okay, simplifying this is a scalar. We can move that in front. So we've got 1/5 minus 2e multiplied by minus 3, and then plus 0 times 4. Okay, simplifying that part 0, this is plus 6e, so 6e over 5, which we can write as 6/5 times e. All right, so that is the slope of this function in the direction of this vector. You know, analogous to what we have here. In fact, why don't we try our luck changing this and see what this tells us? So if I enter that function, so we have exp for e to the power of x squared multiplied by cosine of y. Now our point is 1 comma pi. Okay, so we'll enter that here. And then the vector is -3, 4. So -3, 4, and then I put a y part of it as 0 so that this piece of code works. Let's run this. Okay, it's taking a while. Okay, so here's our visualization. Let's have a look. Seems to just be out of the bound of this, all right? And I can see that we do have 6/5e, but it's had trouble, you know, translating that to something writable because I've joined strings there. All right, so I would just have to extend this, but you can see the point there. You can see the plane, and then you can see the tangent. I just need to extend the range of this, of the plot. Okay, so I'll leave that there, and we'll move on to the next page. Consider the contour diagram of a plane. Z equals mx plus ny plus c. So I feel like I should draw this here in the box. Okay, so there's some axes. Now I might have a plane that looks something like this. Okay, with intersections on the axis like this. All right, so there's my triangle method. All right, now what do the contours look like? Well, in the xy plane, and I probably want to do this so that I can visualize from here to here. Okay, so these would be, so remember they're horizontal slices. So if this is x and this is y, according to what I've drawn here, I've got to cock my head a little bit to think about this. So they look like this, right? They are lines. So these are the contour of that plane. Okay, so let's go ahead and look at this. For n not equal to 0, the contours have slope minus m over n in the xy plane. So yeah, all of these would be the same slope, these contours. The gradient vector, so just calculating the gradient vector, we have m comma n, or mi plus nj. This has slope n over m if m is non-zero. So, and so is perpendicular to the contours, right? So let's indicate that here. This would be grad f at some given point P, right, perpendicular to the contours. It points in the direction of increasing f, all right? So where do you go to increase? So let's try to, it would be like this, right? Grad f would tell you to go that way. You'd be ascending most rapidly up that function there that I've sketched by hand. In fact, the direction in which it points is the direction of greatest slope. We already know that. Okay, consider the function f of xy equals x squared plus y squared. All right, so straight away, let's do a little diagram of this. This is a very easy one to sketch by hand. So it has a point 0, 0, 0, and then it's a bit like a bowl. So something like this, right? So we can see that the bottom is down there at 0, 0, 0. So the contours are circles. This is our Z. Okay, so let's draw the same surface with a contour diagram. So we've got concentric circles. So these are the contours of F, looking something like that. And grad F, now just looking at this, differentiating this partially with respect to x, we get 2x, and then differentiating partially with respect to y gives 2y. So this is grad F. These point radially out, right? These vectors. Radially out from the point x comma y. So something like this. This is grad F at P, where P is this point. Okay, these are perpendicular. Once again, grad F points in the direction of greatest slope from P. All right, so in this, let's see, where have we chosen? I suppose here, and it says go that way, right? So this is grad F in this diagram, and this is P here. So if you would go this way from this point, then you would go up that slope most rapidly. And perpendicular to the contour lines. Okay, so remember what those contour lines are. They are horizontal slices through the surface, so I could sort of draw this as a dashed line through here. That intersection of a horizontal plane with the surface. Okay, so this is perpendicular to tangent of circles at P equals x comma y. Okay, let's take an example, e.g. if I'm looking at the point 1 on root 2, 1 on root 2, all right, what's the z coordinate? It would be, so 1/2 plus 1/2 is 1, all right? So this is a three-dimensional point. Let's say it's there. So if this is P, then this is on the contour x squared plus y squared equals 1, so the unit circle. Okay, let's find that. So it looks something like, here's x, here's y. We've got this circle, x squared plus y squared equals 1. And then we're at this point, okay, where the x and y value are equal. So through the line y equals x. Okay, so now what do we want to do? Let's calculate the slope of the tangent. Okay, so slope of tangent at 1 on root 2 comma 1 on root 2, right? So this is the two-dimensional version of this point, is given by taking dy on dx of this curve right here. But since this curve is given implicitly, we need to do this with an implicit derivative, and that's given by the formula minus f subscript x over f subscript y, where f of x and y is x squared plus y squared minus 1. So I've taken everything to one side so that I have 0 on the other side. All right, so the partial derivative of this with respect to x is 2x. So we've got minus 2x over 2y. Right, and so then dy on dx at the point, this point P, well, since the x and y coordinates are equal in this point, so dy on dx at P is just equal to -1, right? Slope -1. Now let's draw that. So that's like this, right? Slope of the tangent equals -1. I'm sorry if you can't see this, but I hope you can write this clearly on your own page. All right, and then perpendicular to that is a slope 1, right? Being the gradient vector at P. All right, example 3.7. Let T, a function of xy, be 20 minus 4x squared minus y squared. So this describes the temperature on the surface of a metal plate. Okay, so what would this look like? Well, so you might have a metal plate, rectangular, something like this. And then let's draw some isothermals. So curves on which you have the same temperature, something like this. And then of course the metal plate has a boundary, right? So isotherms are these curves here. So they are contours of the surface. All right, maybe I can just quickly give you a little plot of that surface. So plot 3D, 20 minus 4x squared minus y squared Let's have a little look at this. So it looks like this, right? And now I've plotted this within a square box here, right? Whereas here I've got a rectangle. Oh well. So these contours, now let's see if I can write a contour diagram as well while I'm at it. So that's just contour plot, and I need to omit the 3D. Okay, so here we go. So they look like this. These are the contours or isotherms of this metal plate. So what I'm trying to draw here. All right, now let's do some calculations. So in which direction away from the point 2, minus 3 does the temperature increase most rapidly? In which direction is it not changing? All right, so we need to calculate grad T. So differentiating this with respect to x gives us minus 8x, and differentiating partially with respect to y gives minus 2y. So then grad T at the point 2, minus 3, subbing in x is 2, we've got minus 16, and subbing in y is minus 3, we've got 6, plus 6. All right, so this is a vector. Now this tells us the direction to go from the point 2, minus 3 in order to increase in temperature most rapidly. So let's write this out. The temperature increases most rapidly in the direction of the vector minus 16, 6 from the point 2, minus 3. Okay, now in which direction away from the point 2, minus 3 is the temperature not changing? Well, it would be perpendicular to that, right? So for example, here's grad F, and then perpendicular to that, not changing in this direction or this direction. All right, so let's note that, so let, I don't know, vector u be equal to the vector. Now I'm just going to swap these and put a minus sign on one. so that we get a dot product equal to 0, so 6 comma 16, then u dot grad t at 2 minus 3 is equal to 6 dot 16 dot minus 16 6, and I've chosen that so that this dot product is 0. Okay, so in the direction of plus or minus, because you could go either way, 6, 16, or any multiple of it, any scalar multiple of it, there will be no immediate change in the temperature T. Right, and I say no immediate change because look, if you keep going in that direction, you end up on a different isothermal, right? So immediately in this direction there would be no change, right? But as soon as you get over here, you got to calculate again. Okay, so next topic, using the gradient vector to find the maximum and the minimum of a function. So this is an application of the gradient vector. Again, consider f of x, y is x squared plus y squared. So see this figure, so there's a diagram of it. We see that the minimum value 0 of the function occurs when x and y are both 0. Right? And you can see that just from the diagram. We can find where this occurs using the gradient vector, since if there is a local maximum or minimum at the p on the surface, then grad f at p would be the 0 vector. This is analogous to seeking a local maximum or minimum of a function of one variable, right, where you would get slope equals 0 where there's a local max or a local min in that function. So you would solve f dash of x equals 0 for x and use this to find turning point in the function. All right, so let's have a look here. Use the gradient vector to find any local max or min of this surface. We already know the bottom is 0, 0, or 0, 0, 0 in 3D. Right, so grad f is equal to 2x, 2y, the vector. Okay, if this is equal to the 0 vector, then this is equal to 0, 0. So from that, we can set out two scalar equations, equating this to 0 and equating this to 0. So 2x is equal to 0 and 2y is equal to 0, right, as a simultaneous system. So this gives x equal to 0 and y equal to 0. Hence, 0, 0 is what we call a critical point. Okay, now this is a vector, this is a point. So the max and min occur here, we just don't know which one yet. All right, now to classify mathematically whether 0, 0 is a max or a min, what we need to do is calculate second derivatives. So fxx at the critical point 0, 0, fxy at 0, 0, fyx at 0, 0, and fyy at 0, 0. Okay, now the figure here just shows that. So figure 18 shows that the point 0, 0, 0 is a global, not just local, but it's a global minimum. So what we're going to do next is confirm this mathematically by calculating these. Okay, and I think we're going to jump back to that because first we need the main result on this. So a critical point AB of a function f of xy is a point where in which either grad f is 0, 0, the zero vector, or f at AB is not defined. For example, the top of a pyramid or the bottom of an ice cream cone. In order to classify critical points as maxima or minimum, we must introduce the Hessian matrix, which I call H subscript f at AB, or sometimes I just leave off the subscript. It's given by the matrix that has as elements of the matrix those second order partial derivatives. Now the determinant of that is just this times this minus this times this. All right, and I'm calling that delta here. So let f of xy be a function with continuous partial derivatives at the point AB. Let delta E equal the determinant of that Hessian matrix. If the point AB is a critical point, then it can be classified as follows. If the second partial derivative with respect to x, f x at AB is positive and the determinant of this matrix is positive, then the critical point A, B is a local minimum. If fxx at AB is negative and the determinant of that Hessian matrix is positive, then the critical point AB is a local maximum. If the determinant of the Hessian matrix is negative, less than 0, then the critical point is a saddle, much like the one that you sit on. If the determinant of the Hessian matrix is 0, then this test is inconclusive. All right, now note, if the first and the second partial derivatives exist and are continuous, then by Clairaut's theorem, we have f subscript x y is equal to f subscript yx. So those two derivatives are the same in that case, and then what we would get is the determinant of the Hessian matrix at the point AB is equal to f xx at AB times f yy at AB minus f xy at AB squared, right? Because these two would be the same. All right, so now we're going back to classifying that point. Now remember, it looked like this, right? So we already know that this is a minimum. But we're going to use mathematics to classify it. So f subscript x, just looking at that, we have 2x. F subscript y is 2y. F xx is the derivative of this partially with respect to x, which is 2. F yy is the derivative of this partially with respect to y, which is 2. F xy is the derivative of this with respect to y partially, but that's 0. And fyx is the derivative of this partially with respect to x, which again is 0. These two match. So our Hessian matrix is 2, 0, 0, 2. Right? And that does not depend on the point. It's this everywhere. So then the determinant of that, so det of the Hessian matrix, which is equal to 2 times 2 minus 0 times 0. So we've got 4, and that's positive. All right, and so now what we need to do is look at the sign of fxx at 0, 0. So that is equal to 2. That is positive. So the previous page tells us that, so the point 0, 0, 0 is a local minimum. Okay, now how do we know it's a global minimum? So local is locally, as the word suggests. Global is over the entire domain. So the domain of definition of f is all two space, so all pairs of real numbers. So this is how we denote that. The set of real numbers superscript 2 space of real numbers. Okay, and so we can see that away from 0, 0 along any given path, f is increasing. And that is mathematically provable, right? But we're just speaking loosely at this point. All right, so we know that this is increasing, so the point 0, 0, 0 must be a global minimum in addition to being a local minimum. All right, moving on. Example 3.10. Consider the function f mapping 2 space to the real numbers by this quartic function. Find and classify all of the critical points of f of x, y. Okay, so we must solve grad f equals the 0 vector, right? So we need to calculate the partial derivatives. So f subscript x is 4x cubed plus 2 minus 3y plus 3x squared. Okay, so we take that to be equal to 0 given by this. And then we have another one, f subscript y is minus 2y and then minus 3x. And that's equal to 0 given by this. Okay, so solving this system, it's a nonlinear system in variables x and y. We want to solve this by eliminating, say, y, but to do that, we want to take that second equation and solve that for y. So solving minus 2y minus 3x equals 0 for y, and then to sub it in, so we take the 2y over to the right hand side, divide by 2, and then we get y equal to minus 3 over 2x. Okay, substitution into first equation gives us, let's see, subbing that in. So we've got then, where are the y's? There's only one y in it. So we've got 4x cubed plus 2 minus 3 times minus 3 over 2 is plus 9 over 2 times x. Plus 3x squared equals 0. So now I've eliminated y by substitution. And now I want to solve this. So to do that, I would want to multiply throughout by 2, so I get integer coefficients of the x. Okay, so multiplication by 2 gives us 8x cubed plus 6x squared plus 9x plus 4 equals 0. All right, so now you could call this something and you could sub in a value and see that you get 0. So notice, now let's just call this g of x. Notice g of minus 1/2 gives 0, right? So you could sub that in and see that it gives you 0. So that tells you then that 2x plus 1 is a factor of g of x. Okay, and then you could do long division. Okay, so let's do it. What do I need to have up here? So this divided by 2x is 4x squared. Multiply this times this, write it underneath. We've got 8x cubed plus 4x squared. Take a difference. 2x squared plus 9x plus 4. Okay, this divided by this is a single x, isn't it? Yep, single x. Multiply x times this, write it underneath. 2x squared plus x, take a difference, and we've got 8x plus 4. This divided by 2x is 4. 4 times 2x plus 1 is 8x plus 4. 0 remainder. So what that tells us then is that this is equal to 2x plus 1 multiplied by 4x squared plus x plus 4, and that's equal to 0. Now this quadratic polynomial here is irreducible over the real numbers, so it doesn't factor any more over the real numbers. So x equals the root of this minus 1/2 is the only root of that function g of x. All right, so given that, that gives us a unique critical point. Okay, subbing double b, isn't it? So subbing x equal to minus 1/2 into y equals minus 3 over 2x, we've got the point. So what is that? Minus 1/2 times minus 3/2 is 3 over 4. So minus 1/2 and 3/4 is the unique or only critical point of f of x and y. All right, I'm almost out of space. So now for the Hessian, we've got to take second order derivatives. So fxx is, well, where did f of x go? It's here. We're differentiating this with respect to x partially. So we have 12x squared. And then looking at this, that's plus 6x. Okay, now if we were to sub in minus 1/2 into this, we would have 12 times 1/4, which is 3, and then minus 3. So fxx at minus 1/2, 3/4 is 0. Okay, now if we do all the other partial derivatives, we will find that the Hessian, I'm saying that because I'm out of space now, so the Hessian at minus 1/2, and that's because I've done this here. But you could have just believed me in writing that, right? Okay, so the Hessian at this point, this critical point, is 0, minus 3, minus 3, minus 2, and the determinant of that is minus 9, which is negative. So this point minus 1/2, comma 3/4 is a saddle. All right, so we classify it as a saddle. It's neither a max nor a min. In one direction it goes like this, and then the perpendicular direction it would go like this. Okay, and there's the diagram of it. So that saddle, you see how it's curving this way, and then the other way it curves this way. So it's a saddle there. Example 3.11. Find the global max or min of the function f of xy is 3x plus 3y all squared plus 2 on the domain where x and y are between minus 2 and 2. Okay, so let's first draw a little diagram of this. So first I want to draw the domain. Okay, 1 tick, 2 ticks, 1 tick, 2 ticks, 1, 2 this way, 1, 2 this way, and now let's put a a 2 by 2 box around that. Okay, so this is our domain. So the function is defined in this box, right? All right, so now first notice that this is a square. That square is completed, so f of x, y has to be greater or equal to 2 because squares are positive or 0. So the lowest that this could be is 2. And so this achieves 2 when the inside of that square is 0. So when 3x plus 3y is 0, so when y is equal to minus x. Okay, so where is that on here? Well, we've got this line, looks like this, passing through 0, 0 and hitting these corner points. Okay, so we already know that it's going to probably be minimum along this line here in that box. All right, we already know that. It's going to achieve a minimum of 2 there, but let's use the tools we've learned to do this now. Okay, so grad f is equal to, and we've got to use the chain rule to calculate this. So pulling the 2 down, so we've got 2 times 3x plus 3y to the power of 1 multiplied by the partial derivative with respect to x of 3x plus 3y. And then similarly 2 times 3x plus 3y times the partial derivative with respect to y of 3x plus 3y. Okay, now differentiating that, we've got just a 3 for this, so 3 times 2 is 6, and then times another 3, 6 times 3 is 18. So we've got 18x plus 18y, and then similarly here, also 18x plus 18y. All right, so there's our gradient vector. Now, this is equal to the 0 vector when xy is a critical point. Meaning a point where we could have a maximum or a minimum locally. Okay, so let's look at this equation. Well, this gives the system 18x plus 18y is 0, matching this and this, and 18x plus 18y is 0, matching this and this. All right, but we can see what happens. Divide throughout by 18. These two coincide, and it just gives us y equals minus x. And that is a line of critical points. So just as we suspected from this calculation here, we've got a line of critical points. All right, so now to classify, let's take the Hessian. So Hessian of f. Now differentiating this with respect to x gives us fxx. So we've got 18. Differentiating this with respect to y also gives us 18. And similarly, we've got 18s everywhere. Okay, so then the determinant of this matrix is 18 times 18 minus 18 times 18, and of course that's 0. So what we learn then is that the test is inconclusive. All right, so how do we determine what the max and min are? Well, what we've got to do is look at the boundary of the domain, because the max and min occur on the boundary of the domain. Boundary of domain, since the test is inconclusive. Okay, so along, let's start with x equals 2, so along the top. So f of 2 comma y, subbing in 2 here, we have 6 plus 3y squared plus 2. Okay, f subscript y along that line is equal to 0 when x is equal to 2 and y is equal to minus 2. All right, so f minus 2y, so along the bottom of that domain, we have then minus 6 plus 3y squared plus 2, and f subscript y along that line is 0 when x is equal to minus 2 and y is equal to 2. Okay, continuing now, let's do the, oh no, I said bottom and top, right? But I meant left and right. Okay, so now we're going to do bottom and top, or top and bottom. fx comma 2 is equal to 3x plus 6 all squared plus 2, and f subscript x, x2 is 0 when x is equal to minus 2 and y is equal to 2. So just like this, right? Similarly, when we do fx minus 2, we'll get the same or something similar here, and this occurs when x is equal to 2 and y is equal to minus 2. All right, so what we're seeing then is that the global max and global min are at these 2 points. So when we sub those in, we will see that f of 2 comma minus 2 is equal to 2, which is equal to f of minus 2 comma 2. All right, so these are f equals 2 and f equals 2 here and here. And those are our maximum, so global max. Okay.